Welcome to the Introduction to Quantum Computation Basics. This presentation will cover quantum Turing machines and their complexity. Prepare to dive into the fascinating world of quantum computing. Now let's compare classical and quantum computing. In classical computing, information is stored in bits, which can be either 0 or 1, representing definite states. Quantum computing, on the other hand, uses qubits. Qubits can be in a state of 0, 1, or a superposition of both, denoted as psi, representing probabilistic quantum states. This fundamental difference allows quantum computers to perform certain calculations much more efficiently than classical computers. Let's delve deeper into quantum superposition. A qubit can exist in a superposition of both 0 and 1 states simultaneously. This state is represented by the equation psi equals alpha times 0 plus beta times 1. Alpha and beta are complex numbers that define the probability amplitudes of the qubit being in the 0 or 1 state, respectively. The sum of the squares of the absolute values of alpha and beta must equal 1, indicating that the qubit will be in either the 0 or 1 state when measured, with probabilities determined by these amplitudes. Moving on to the Classical Turing Machine, which is a theoretical computing device, which manipulates symbols on an infinite tape based on a set of rules. It serves as a fundamental model for classical computation. The essential components include an infinite tape divided into cells, a read-write head to access the tape, a finite state control that dictates the machine's actions, and a transition function that specifies how the machine changes state and modifies the tape. Now, let's talk about the Quantum Turing Machine, which is a quantum extension of the Classical Turing Machine that operates on quantum states. It incorporates quantum principles to enhance computational capabilities. Key features include a quantum tape that can exist in superposition, a quantum head position that can also be in superposition, the ability for the machine to be in a superposition of states, and the use of unitary evolution to perform computations. Now let's explore quantum complexity classes. We'll discuss three important classes: P, BQP, and NP. First, P represents problems solvable in polynomial time by classical computers, such as sorting, searching, and finding the shortest path. Next, BQP denotes problems that can be solved efficiently by quantum computers, including factoring, discrete logarithms, and quantum simulations. Lastly, NP includes problems for which a solution can be verified in polynomial time, such as satisfiability or SAT, the traveling salesman problem, and graph coloring. Now let's examine famous quantum algorithms. We'll focus on Shor's algorithm and Grover's algorithm. Shor's algorithm is used for integer factorization. It has a time complexity of big O of log n cubed, providing an exponential speedup over classical algorithms. Grover's algorithm is used for searching an unsorted database. It has a time complexity of big O of the square root of n, which gives a quadratic speedup compared to classical search algorithms. Finally, let's consider the quantum complexity landscape in future questions. Key questions remain, such as the relationship between the complexity classes P and BQP, whether BQP is included in NP, the limits of quantum advantage, and the challenges of physical implementation. The quantum computational landscape continues to evolve with new discoveries. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.